So here's a coordinate proof with regular numerical coordinates, 1, 5, 6, 2, 3, -3, and -2, 0. So you see I have that plotted over on the grid, and it does appear to be a square, but we're asked to prove that that is a square. And the way I went about that, in short order here, I found the slope of AB to be -3/5 and the slope of DC, opposite, to be -3/5. You can use a slope formula, you can count rise over run, whatever it takes to show that it's both -3/5. And I can see in pink there I wrote parallel because they have equal slopes. So there's one set of parallel sides. Then I found the slope of DA, which was 5/3. Opposite that was CB. That was also a slope of 5/3. Again, rise over run, slope formula. Either way, I found those to be the same, which means again I had a second set of parallel sides because I had equal slopes. Now, if you compare those two different slopes I came up with, -3/5 and 5/3, they are negative reciprocals, which means those segments were perpendicular and form a 90-degree angle, something that you need in a square. So now I have two sets of parallel sides. I have at least one 90-degree angle, and if you look at the sheet that was provided on the PDF, I need one more piece of information to prove that it is a square, and that would be either 4 congruent sides or just prove that 2 consecutive sides in a row around a corner are both the same. And that's what I did in green down here. I used the distance formula to find the length of AB, and it came out to be an odd number, no pun intended, but radical 34. And don't be afraid about coming out radicals or not even. All you're trying to do is prove that another side is the same length. And that came out to be radical 34 as well, using the distance formula. So now I know that I have a square. And if you look at the clinching statement at the end there, ABCD is a square because it has 2 pairs of parallel sides, a 90-degree angle, and 2 consecutive sides which are the same length. Here I'm asked to write an equation of a line that is parallel to 3y equals 4x plus 9 and passes through a certain point, -3, 2. Now that isn't in y equals mx plus b form, that line, but you can see that I divided through by 3, and just with that one step I put it into y equals mx plus b form. So I know that my slope is 4/3 now. And since I'm looking for a line that's parallel to that, I want that same slope in my new line because parallel slopes will be equal. Now I'm asked to write the equation of a line, so I jotted down y equals mx plus b, and I'm going to substitute in what I know. I know everything except for b, which is going to help me find my new line. I know they want me to use the point -3, 2. Well, the y coordinate of that is 2, and the x coordinate of that is -3. And I know I have the slope already found, which is 4/3. I'll clean this up a little bit, and I get 2 equals -4 plus b. I add the 4 back over, and I get that my y-intercept is 6. Well, now coupled with the fact that I knew the slope already right there, 4/3, and that I have the y-intercept, I now can write my final equation. Y equals 4/3 x plus 6. This next question has a tricky part and an easier part. I like the fact that it's the origin because the origin is 0, 0, and when I plug zeros into equations, it tends to make things easy because the factor of 0 usually makes equations very simple. However, I don't like the fact that this line that they gave me is in such a crazy looking form here. So I want to solve it for y because I'm most familiar with that form. So the first thing I'm going to do is subtract 3x to the other side and then divide through by 5, and now y is isolated. I have a slope of -3/5 and a y-intercept of 3. Now it said it needs to make a right angle with that line. A right angle means 90 degrees, which means perpendicular. So I don't want to use the slope of -3/5. Instead I want to use positive 5/3. It's negative reciprocal. So this time I did not use the identical slope like I did in the last problem because that was parallel. This is perpendicular, so I flipped it and I negated it. Now I could go through and did what I did on the last problem and set up y equals mx plus b and plug everything in, but because I have 0, 0, I know it's going to go through the origin, and the origin is on the y-axis, so the y-intercept is 0. So it's just going to be y equals 5/3 x plus 0, or just y equals 5/3 x. Now for every example in number 11, we're using the point radical 5, 3/4. Strange looking odd point, but we're just talking about parallel and perpendicular lines here. In example A, it wants us to find a line parallel to y equals 1/2. Well, y equals 1/2 cuts through the y-axis at 1/2, which means it's a horizontal line. So we're always going to start with the same thing. Y equals the y-coordinate that we were given, which is 3/4. In question B, perpendicular to the x-axis means it will look like the y-axis, which means it's going to cut through the x-axis. So I'm going to say it's going to cut through the x-axis at the x-coordinate I was given, radical 5. In question C, parallel to x equals 4 means it's going to start off, just like I did in letter A, it's going to start off the same, x equals the x-coordinate. So the answer turns out to be the same as it was in B. Now in question D, perpendicular to x equals 5. Now x equals 5 would cut through the x-axis, so I want to cut through the y-axis at the y-coordinate, which it gave me was 3/4. So all of those lines, they're vertical or horizontal, and they all have to go through the point radical 5, 3/4. Now in number 12, it wants us to decide whether the lines that are given are parallel to each other, perpendicular to each other, or neither. They don't meet at a 90-degree angle, or they're not parallel either. So if you look at the two lines, I solved them both for y. I solved the top one for y in blue, and I solved the bottom one for y in red. And if you look closely, the slope after I solved for y and put it in y equals mx plus b form, the slopes were both 3. So if the slopes are the same, I decided that they were parallel. In question B, you can see where I solved for the slope, I solved for y and determined one slope to be -3/2 and the other to be 3/2. Well, that's not the same, nor is it a negative reciprocal. So I decided that they are neither parallel or perpendicular. In question C, you just move the 8 over and subtract it and you get x equals 7. That's a vertical line. And y equals pi, it cuts through the y-axis. That's a horizontal line. Well, vertical and horizontal lines are perpendicular. I lost the r, I'm perpendicular there. So questions 13 and 14 are very similar. It's asking me to write the equation of a perpendicular bisector of a segment that connects 4, 2 and 8, 10. Now, perpendicular bisector is nothing more than a line that goes through the midpoint. That's the bisector part. We know how to find midpoint. And it's also perpendicular, which means negative reciprocal slope. So we know both of those things. The fancy term is perpendicular bisector. The first thing I did was find the midpoint of the given segment, and that turned out to be 6, 6. So I know it has to go through the point 6, 6. Next thing I did was work with the slope, and I determined the slope of the segment containing 4, 2 and 8, 10 to be 2. But I don't want that slope, I want a perpendicular slope, so I did a negative reciprocal, and I ended up with a slope of -1/2 that I want to use. So down here, in my y equals mx plus b work, I plugged in the point 6, 6 for x and y. I plugged in the slope of -1/2. I solved for b and got 9. And then I plugged in my slope and my y-intercept and determined the equation to be y equals -1/2 x plus 9. Now, number 14 is very similar. It has an ugly looking fraction in it that makes things a little more complicated, but I found the midpoint, -1, -5/2. I found the slope to be 1/8, but then I did a negative reciprocal because I want a perpendicular slope. Then I took the x and y coordinate from the midpoint, the -8 from the slope, and I plugged it into y equals mx plus b, and I got a final answer of y equals -8x plus 21/2. So here we're asked to find the area of this pentagon, and because it's on a coordinate grid, what I can do is box it in with some sort of brown rectangle here, which is 6 by 5. Now the area of a 6 by 5 rectangle is 30. So this would be the equivalent of taking this rectangle and then cutting off this first triangle, this second triangle, this third triangle, and this fourth triangle, and once those are lopped off right here, I'll have what's left, which is just my pentagon. So we determined the area of the rectangle was 30, and then right here I have all 4 triangles that I identified. This first triangle was 3 by 2, so half of 3 by 2 is 3. The second triangle was identical to that, so another 3. The third triangle was 1 by 3, so half 1 times 3, which is 1.5, and triangle 4 was identical to that. So my 4 triangles are 3, 3, 1.5, and 1.5. So really here's a pictorial representation of what I'm really doing. I'm taking the pentagon, and to find the area I start with the rectangle and I chop off or subtract all 4 triangles, and that leaves me with 21 units squared for the pentagon. Here's the same thing with a simpler quadrilateral. This is actually an easier problem. There's less steps to handle here. But I had this quadrilateral that was somewhat irregular, and I boxed it in as tight as I could with this brown rectangle. Rectangles are easy to find the area of because it's just length times width. So you see I have 7 and 8. Well, 7 times 8 is 56 for the starter rectangle. And then this time I only actually had 2 triangles. One on the right and one on the left. 1 and 2 here. Each of them were 7 by 2. So I have half 7 by 2, half 7 by 2. So each triangle was an area of 7. So I start with my rectangle of 56, subtract the 2 7s out, and I'm left with 42 units squared for the quadrilateral. So this problem is very similar, except it's tricky in the sense that if you look closely here, the triangle that I had to plot myself had an obtuse angle in it, and that obtuse angle right here forced me to have this leftover rectangle here, but that's okay because I know how to find the area of a rectangle. I'll just chop that off too. So I started with this initial giant brown rectangle, which was 9 times 6. And 9 times 6 we know is 54. The first thing I did was chop off this big triangle here on the bottom left side. Also 9 by 6, but it's half of 9 times 6, which is 54, which makes it 27. Then the second triangle I subtracted was this top sliver up here, which was an area of 12. The third was this tiny little triangle here that was 3 by 1, which is an area of 1.5. And then in blue you can see I represented that rectangle there, which was 3 by 1, which is 3. Starting with 54 and subtracting out the 27, the 12, and the 1.5 triangles, and then the 3 for the rectangle, I ended up with 10.5 units squared.